Greetings. According to the theory of groups, element of a group has a certain order, and this order is given by the power it has to be raised to. That's kind of a way to say that how many times this element has to be put into operation that's defined for the group with itself until the result of this repeated operation of this element with itself reaches the identity element as a result. So the order of element is basically the minimal value of some element, let's say a to the n, so that it's equal to e, which denotes in general the identity element of a group. And the n is the minimal positive integer. So the minimal positive integer n, such that how many times I have to put into operation with itself the element a that I consider, and that will be the order of a. This is how it's denoted, order of a. This is the way it's denoted. So basically in this case I'll be doing it for permutation group. So just like was done in previous video, there was this permutation group of f1 was 1, 2, 3, 1, 2, 3. That's the identity of that group, by the way, because it has same inputs and outputs. If one wants to get closer look at this idea of permutation groups, the previous video I did on it, slightly closer. And the other permutations are all the different options where still 1 till 3 is on the top, but on the bottom there are different permutations of the three numbers 1, 2, 3. So 1, 2, 3 all along, and f6 again until f6, 1, 2, 3. Just these three numbers, their positions are changed. So here it was 1, 2, 3. Here I can do 1, 3, 2. Then I can do start with 2 and do 3, 1, 2, 1, 3, and then start with 3, 3, 1, 2, and 3, 2, 1. These are all the different permutations of these three numbers on the bottom, in what order they can be, in what linear order they are positioned. Now, what I can look at is the order of these individual members or these individual elements, because f1 up until f6 together create the permutation group of these 3, 1, 2, 3. And so I can also ask in this context, what is the order of, let's say, one of these functions? So how to find it out? Well, we'll do it in an exact manner, just show concretely how it's done here. So for example, for f3, so order of f3, what will it be? Well, it should be the smallest positive integer such that f3 in operation with itself n times, or in the common notation f3 to the n will equal to the identity element. And the identity element for this group, well, first of all, one has to realize what kind of group it is, therefore what kind of identity element it will have. This is permutation group. The identity element is this function that takes 1 into 1, 2 into 2, and 3 into 3. That means that f1 of 1 is 1, f2 of 2 is 2, just like f1 of 2 is 2, and f1 of 3 is 3. For each of these three inputs, it is the same value. Now, these other ones are not the same. So the identity element of this group, because the elements of this group are these 6 slightly different functions, the identity element is this identity function which does not change the input into output into a different number. It just leaves it. So basically, how can one do this? Is put this exact function we chose to find the order of into operation with itself. That means 1, 2, 3. I can delete the rest of these because we'll just be using f3. So f3 is this, and we're looking for the order of it until it reaches the f1, because 1, 2, 3 and 1, 2, 3 in the bottom as well. So what is the order of it? Well, one can start by first of all realizing that the first time this is mentioned, this is the first. So if already now it was, if we chose f1, and already now it would be 1, 2, 3, 1, 2, 3, then it would have order 1. But because it's not the identity element, it's not the 1, 2, 3, 1, 2, 3 case function, it is f3, which is 1, 2, 3, 2, 3, 1, we have to determine how many times it has to be put. So at minimum it will be order 2. But still it's not certain, and quite unlikely that already in order 2 it will be enough that the result of this will be in function composition will be the 1, 2, 3, 1, 2, 3 function. So I take it again and put it into operation with itself. So what that gives is basically operation with this group permutation is is function composition. And the point is that one has to take these values first from the second row and then put it into the first row of the first function. So the order is now doesn't matter because they're both same. But still, if they were not same, what one will do when this is in composition with this function, the usual order it is done in, the usual way it is viewed means one looks for 1, that means that one looks for what 1 means in the second function, that's 2, and then one plugs in this 2 here and gets 3. So 1 would give 2, but it will get 2 here, and the result will be 3. Therefore, the result of this composition, at least for the first number, for the number 1, will be 3. So to do it is 1, 2, 3 are the inputs, those will not change. But what will change, how I do this, how this will be done is basically 1 goes to 2 and 2 goes to 3, therefore this is 3. 2 goes to 3, but I have to plug this result into the first one, so 3 goes to 1, this is 1. So 3, 1, and 3 goes to 1, and 1 goes to 2, so it's 2. Alright, so this is already 2 times in operation, so this function has already appeared 2 times in a row in a chain operation with itself, and still is not equal to 1, 2, 3, 1, 2, 3. Now it's 3, 1, 2. And so we can continue. We can continue in the following way, that basically 1, 2, 3, 3, 1, 2 will be further put into operation with this 1, 2, 3, 2, 3, 1. Alright? And now we know that it has already repeated 2 times. So now the order will be at least 2. And maybe 3, maybe even more, we will see. So, 1, 2, 3, 3, 1, 2 is the result so far for the repetition 2 times. And that is further put in operation with the same function we're looking for the order of. So, again, the same way of composing the 2 functions. 1 goes to 2, 2 goes to 1. So 1 is 1. Nice. That seems like it's already probably going to be at the final stage. 2 goes to 3, 3 goes to 2. So 2 is 2. Good. And 3 goes to 1, 1 goes to 3, that is 3, 3. That means that now we've gotten to the identity element, which is the F1, because F1 was defined as the identity of these 6 functions, 1, 2, 3, the identity element in this group of functions, or in other words, this group of permutations, or permutation group. Alright, so now that we've already reached, I can delete this and look at how many times it took to be able to finally get to this element. So, what was looked for was the order of, if this is F3, how many times it had to be put into operation with itself. That's this question mark. So, what we had to do is do it with itself once and then once again. And of course, associativity, so this was namely done. First we got this result and then put it into operation with the F3 once again. One could also see this in the other way, that the parentheses would go this way, but in even more concrete terms, we did this. 2, 3, 1 with the same 2 more times. And because this was 3 times, the first one was this one, the second one was the second one, and this one was third one, it had to go on, it had to be put into operation with itself in 3 instances of itself. That means that the order of F3 is 3. Because only after the third instance of it, it finally got equal to 1, 2, 3, 1, 2, 3, which is the identity element of this group that we've been looking for.